Okay, let's get started. Why am I adjusting it? I was just in this room. Okay. All right, let's get started. So we left off here last lecture. We got a lot to go through. I think we can mostly get caught up. We almost got all the way caught up in the other lecture. On Wednesday, the cookies lecture is a little bit light, so we'll definitely get caught up by Wednesday. So we left off last time. Very quickly at the end, I said, don't forget your dash U. I want to elaborate that on a little bit on that before we move forward. But this dash U is going to print out your Python standard out and standard error unbuffered. When you run your Python code inside a Docker container, Docker likes to buffer your outputs, where if you run it with Python, you see all your output. When you run it in Docker, you just don't see anything that's printed to the screen or your error messages, which is generally bad for debugging purposes. You want to see, like, when you, the first line of your main method says listening on port whatever, and you don't even see that line. It's just very nerve-wracking. It's very anxiety-inducing. Like, I can't even see that. What the hell is going on here? It's because you're, most likely, I should say, it's because your Python output is being buffered by Docker. So if you add this dash U, the dash U is for unbuffered. It's not going to do that, and you'll actually see your output, which is generally a good thing. So don't forget that dash U. However you're getting your Docker file, I suspect most of you will just copy it from the slides. Please, when you're copying it from the slides, which I do allow, whenever I give you code in lecture, you're allowed to use it in your assignments. But make sure you make any necessary changes and fit what I have here to your specific needs. And part of that is, don't forget that dash U. Just copy that dash U. Please have that dash U. When I have office hour questions and the dash U is not there, it's one of the first things I look for when we have the output not even being displayed. Just make sure that dash U is there. Okay. Then when we build a container, I'm going to go kind of quick through these next two slides because we're not actually going to do this in this class. It's not required anyway. But to build an image, we're going to use docker build -t, whatever you want to name your image, and then dot. That trailing dot is not a typo. That's very important. That's specifying the directory where Docker should look for a Docker file to be able to build your container. And then, big deal, we have a Docker image, or build your image, I meant to say. A big deal, we have a Docker image, but we actually want our Docker containers. For that, we're going to use the run command. We're going to use -p to map a local port to a port inside the container, which we'll talk about a bit more when we get to Docker Compose. But we're going to map a local port. For our purposes, that'll be 8080. Every homework assignment says listen on port 8080. The local port 8080 mapped to a port inside the container. In this example, the app was running on port 8000. So we're going to map local port on our device 8080 to port 8000 inside the container. So when we get a request for localhost 8080, we're going to zap that into the container at port 8000. If you don't want to think about that stuff, a lot of students like to just use 8080 everywhere, inside and outside the container. Then you don't have to think about the ports too much. But this is what mapping ports is doing, mapping a local port to a port inside the container. And image name should match whatever image name you use to build. And you can hit this with a -d. This means detached mode. Run this in detached mode. This is if you want to run your container in the background. If you don't have the -d, which I recommend not using this option for development purposes, it'll give you all of the output of your container in your terminal, but it'll hold your terminal hostage, and as soon as you X out or Control-C out of that, it's going to stop your container and stop your app. When you go to deploy, you add this -d, run your app in the background, and it runs forever and doesn't hold your terminal hostage, so you can just run it forever for all of your users. Then you go to localhost 8000. Okay. And when in your code, wherever, if you're following any documentation or anything, you're going to see listen on localhost. Localhost should be the host for your app. So when you start your TCP socket server, you're going to start on localhost. That's what the documentation will say. When you're using Docker, make sure you switch localhost to 0000 I believe in the handout code, I just put this as 0000 just so I don't have to deal with so many office hour questions about this. It's not really pertinent to your understanding of web apps. But make sure that's 0000 because if it's localhost instead of that, then your app will not be accessible from outside the container. 0000 is going to make your app accessible from the outside world, from outside of the Docker Compose ecosystem. So make sure you have that in your code. That's not a typo. It needs to be zeros. Localhost will not work. Or let me rephrase that. Localhost will work when you run it with Python, and then when you run it in Docker, it's not going to work. So, which is a very frustrating problem to have. When it works in Python, when you do Python server.py, but when you do Docker Compose up, as we'll see in a second, it doesn't work. Very frustrating, and this is one of the leading causes of that discrepancy. Okay, now Docker Compose. Docker Compose is how we're actually going to run our apps. What Docker Compose does for us is a few things. One, it lets us run multiple containers. That's going to be very important starting next week. I forget when. I think next week, Monday, when we start using a database. It's going to be very important because we'll need to run a database and our app as two separate processes, and we're going to run those as two separate containers. Docker Compose is going to let us write a single app with multiple containers that are started with one command. We're going to do Docker Compose up, and that just starts everything. Everything just spins up, and it's great. So one, able to run multiple containers, and two, it's going to set all of our configuration up. We're going to specify all our configuration in Docker Compose, and those few slides we just saw a minute ago of Docker build -t, an image name, directory, then Docker run -p, local port, host, container port, and then image name. We're going to take all of those command line parameters that we gave in those two commands, stuff them into our Docker Compose configuration, and be able to build our images and run our containers with this one command. So we're going to take all that configuration that was command line inputs as of 2 minutes ago, and we're going to stuff those in a configuration file so we only have one command to run our app, which is Docker Compose up. We're going to do Docker Compose up to run everything, and highly recommend, I can't even say recommended, do this. Do --build --force recreate on your Docker Compose up command, and this is going to force Docker Compose to rebuild your images and restart your containers. Without these commands, in the situation that you're all going to be in when you're using Docker Compose, is you're going to run Docker Compose, you're going to spin up your app, you're going to notice a bug, or maybe you just wanted to test LO2 and you didn't do LO3 yet, or the AOs, and you want to update your code and then run Docker Compose again and see the changes. If you don't have the --build --force recreate, you won't see your changes. You're only going to see the first image that was built. You're not going to see any changes you made to the code. So add this --build --force recreate, which will tell Docker Compose, hey, rebuild the image and start the new container based on my new updated code. Don't use the old container because that's out of date already. So Docker Compose up is only going to be good for one time. If you're one-shotting every homework, fine, I guess. If you could do that, yes, that's awesome. Most normal human beings won't be doing that. So --build --force recreate. Personally, I just always use this as my command. I never do Docker Compose up because there's no reason to. And let's look at this Docker Compose.yaml file. This is our file which is going to store the Docker Compose configuration. So we have the Docker file for the Docker configuration, and Docker Compose is going to be in a Docker Compose.yaml file. Docker Compose is part of Docker. It's not a separate installation. It actually used to be. It's part of Docker now. It's actually an extra command in Docker. It's Docker and then Compose instead of Docker build, Docker run. Docker Compose is just another Docker command. So it's part of Docker itself. Docker Compose.yaml. If you haven't seen the YAML format before, here it is. That's YAML. YAML is solving the same solution as JSON. So we have key value stores, we have arrays, we have strings, we have numbers, all the same types as JSON. I think it's one. It might be one-to-one. It might not be. I don't know. But maybe they do nulls different or something. I don't know. but it's the same solution that's being solved, is that we can represent very complex information and nested data structures in one text format. That's what we want. The difference between the two is YAML is more human readable and JSON is more machine readable. So with configuration files, the industry tends towards YAML. And for sending information over the internet or two pieces of software communicating to each other, we tend to prefer JSON. So YAML, indentation matters. We have version and services on the same level, and then app is part of services, and build and ports is part of app. So the white space does matter in YAML files, which is part of what makes it more human readable as opposed to machine readable. So that's the YAML format in a really quick nutshell. No, I should have noticed this earlier. Son of a bitch. I thought it was weird that the last two lectures didn't send a single message in the lecture channel. It's because I was connected to UB Connect, which just doesn't work, but my phone always wants to connect to that one. Wi-Fi. It's always Wi-Fi issues. Oh, the questions I missed. Oh, man. Hi, Midget. Hi. All right, so I still got to keep on track. That's how I made such good pace in the other two lectures, too, because I was unintentionally ignoring chat. All right, so the first line of our Docker Compose file is the version number. And the version number, 3 has been doing everything it needs to do for me. I don't even know 4 exists yet. 3 might still be the latest. I don't know. But it's the version of Docker Compose configuration file that you're using. So if there is something beyond 3 and you want to use the latest and greatest features, use something else. Ever since I've been using Docker Compose, I've been using version 3, and it's been serving my needs perfectly fine. But if you just do version 3, I think you'll be fine as well. Services is a list of services that you're going to build with this Docker Compose file. This is a list of the images/containers that this file is going to build and run. So each service is going to be a separate container that's going to be run to support your app. Right now we only have 1, but once we add databases, we're going to have 2 containers to run our app. And by the end of the semester, we'll have 3 containers to run our single app. Each service has a name. This name is whatever you want to give it. I named it app because, it's my app. It's easy to name. Plus, I think a lot of documentation calls the app just app. If you want to call it web app or my cool app, whatever you want to name it, that's fine. But this name has to be consistent. Whatever you name it here, just remember what you do name it. So app is what I call mine. This is the only word, at least the word in dark blue, that is a name that you choose. Version, services, build, and ports. Those are all keywords that Docker Compose is looking for. App is the one that I name whatever the hell I want, or whatever the hell you want. You name it whatever you want in your Docker Compose file. Build dot. We saw dot. This is the third time we're seeing dot. First we saw copy dot dot, where dot was specifying directories, the current working directory. We saw Docker build -t image name and then the trailing dot. This is doing the same thing as the build. The trailing dot was saying, look in this current directory for a Docker file and use that Docker file to build the image. Same thing here. We're specifying the directory where we're going to build that image. So we're taking all the command line parameters from the build and run commands and putting them in this configuration file. The dot is look in this directory. So I'm going to have my Docker Compose.yaml file and my Docker file in the same directory in this example. And my Docker Compose file is going to say, look in this directory for a Docker file to be able to build this image, and then build an image based on that Docker file. If I want to put my Docker file in a different directory, I would change build to like / the directory for my app, and then if that directory has a Docker file in it, it's going to use that Docker file instead. I'm just going to put these files in the same directory. So dot. That's all I need is one single character, dot. use this current directory. And then ports. This is the same as that -p and mapping the ports that we did in the run command, except we're going to specify this in the Docker Compose file. So ports, and then map 8080 to 8000. This is a list for what it's worth, so I could map multiple pairs here. But this is going to map port 8080 on my device to port 8000 inside the container. There's a tricky line, and I want to explain that more. I want to talk about that more. But I'll get to that in a couple slides and explain that further. But for now, any questions on the Docker Compose format, the structure of this file? If it's buffered, doesn't it eventually release the buffer into the console? No, unfortunately. So if the buffer doesn't fill up, it never dumps out the buffer. So unless you fill up the buffer, then it'll start showing you output. And when you Control-C out of Docker Compose, it's just going to end that process with all your output still in the buffer and never display it to you. So unless you're printing out a lot of stuff, you're never going to see anything if it's buffered. What's the difference between print the result in the main method and unit testing for variety to verify the answer? I think that's a little outdated, but. All right, so we're mapping 8080 on my machine to 8000 in the container for this example. In this example, I'm running a node.js app inside the container, which would be listening on port 8000. I didn't show the code for that. I don't think it's super relevant. But somewhere in there, I would say listen on port on host 0000 port 8000. In the handout code, I think I just set it to 8080. I don't remember these days in the handout code. I guess we could check in like 1 second. Nah, I don't want to. But the second number is whatever port your app is running on inside the container. If yours isn't 8000, you should change that number. So going back to what I said before, fine, take my Docker Compose file, take my Docker file, but make sure you fit them to your needs. Whatever needs to change to fit your app needs to change. If you don't have a file named requirements.txt, then that line's going to give you an error. If your app isn't listening on port 8000, this isn't going to work for you. Make sure you're making any necessary changes. You have to understand what these files are doing so you can make those changes. So this means this. The buffer. I don't know. I don't know if there's a way to change the size of that buffer. I guess we change it to 0 by doing unbuffered. But if you did want buffering, I don't know if you can change that. There might be some Python environment variable that changes it. I don't know. I don't know off the top of my head. So what this means, mapping port 8080 on localhost to port 8000 in the container, it's this with this beautiful little image here. So when we get a request for localhost 8080, this is how we're going to access your app. The testing procedures on every testing procedure for every objective will say go to a browser and go to localhost 8080. When we get that request for localhost 8080, that's going to your laptop. We can't access this container directly. We can't just go to that container. It's not going to work for us. But we'll go to localhost 8080, and when we ran our app on Docker Compose on our laptop, and we told our laptop, hey, I want to map 8080 to 8000. What that did was told the laptop to give port 8080 to Docker Compose. Said, hey, port 8080, I'm reserving for you. Anything I get, any communication I get on port 8080, I'm sending to you, Docker Compose. And then Docker Compose is going to read the second number, the 8000, and Docker Compose is going to say, okay, whenever I get a message over port 8080, whenever you send that to me, I'm going to send it to this container on port 8000. So inside the container, your app is going to see a request for 8000. Outside of the container, the request is for port 8080. So someone sends a request, which is usually going to be you or the TA during testing and development. For localhost 8080, The laptop says, okay, I gave 8080 to Docker Compose, so Docker Compose, do your thing. Docker Compose is going to convert that to your app, a request for your app, which it will use the host name that you gave it as the service name in the Docker Compose.yaml file, port 8000, because we mapped 8080 to 8000, and then your app gets that request on port 8000. Yeah. We don't need two different port numbers. So if you want to use 8080 in both inside and outside the container, that's fine. But it's nice that we have this option. And in cases, there are cases in the future where you'll want to have different port numbers. For reasons, I guess. You'll definitely want different port numbers in localhost. Here, I'll answer a little better. So on my server where I'm running 116, CSE116.com, CSE312.com, and a few other sites, I have multiple sites running on the same machine, the same device. And that device can only listen on port 80 and 443 for requests from the outside world. So I need to run multiple apps on those same ports. So I have a way to listen for those ports. I got to try and not go on too much of a tangent here. I'm listening on those ports, so my local ports 80 and 443, and then I have to map that to my containers, to different ports inside my containers, which, that didn't actually get the point. I have to explain a little bit more. I'm listening to... Oh, that does get the point. So I'm always listening on ports 80 and 443, no matter which container I'm listening for. So those ports have to be mapping to multiple. I guess technically it doesn't have to. It's a bad example. But I do have each app inside each container running on a different local port, and then I'm forwarding 80 and 443. I'm messing this up. I'm starting over, but we're doing this. So I'm listening on port 80 and 443, that's all I can do. And I'm getting requests for different apps, different host names. Then I have an instance of Nginx, which is getting those requests and looking for the host name that's being requested, and then forwarding those requests to different local ports. So I have to have a different local port for every single app that I'm running. But each one of my apps inside the container, I'm using either 8000 or 880. I just have a consistent port number that I run for every single app when I'm developing. So when I go inside the container, it's always going to be like 8000 or 8080, whichever one I chose. But outside the containers, since I have to have multiple ports, one for each app that I distribute, I get the 80 and 443, and then that gets distributed to whatever local port I use for each app to be able to get these to different apps. And then inside the container, it's all the same port number. So situations like that where I need to reuse local port numbers, or I can't reuse local port numbers that I need multiples of, I'm going to map different local port numbers to the same port number inside each container. So I can't just have everything running on 8080 because I just can't do that with multiple apps. I hope that kind of made sense. We got there in the end. I should have just said when you want to run multiple apps on the same device and left it at that. But here we are. We made it on the other end anyway. All right, so we use this file. That's our Docker Compose.yaml file. Docker Compose reads this file and then builds our app. And to run this, Docker Compose up, but make sure you have that build force recreate on there. And when you go to deploy, the only time this will really come in handy in the course is for your group project when you actually go to deploy your app. Then that's when you want to hit it with the -D. It takes the same flag as Docker did when we ran a container. Hit it with the -D. That'll run in the background forever. So you don't have to have your terminal open the whole time. And then get a broken pipe, and then your app crashes. You don't want that. -D will run in the background forever. And then Docker Compose restart is going to restart your container. That'll be in some testing procedure, so I want to make sure I mention it when we restart your app, and then make sure it still works. And then I already talked about this earlier. Okay, any questions on Docker? Any other questions about that? All right, let's get into encodings. Okay, ones and zeros. We talked about this before. The internet can only send ones and zeros. That's it. That's all we got. And it's up to us to make sense of those ones and zeros. So how do we do that? Which is, it's tricky, but we have answers to this. So the first answers that we saw, very briefly, but we saw the IP headers and the TCP headers. What those headers did is directly said these ones and zeros mean these things. If you read the first 4 ones and zeros are going to be the HTTP version number, the next however many are this, the next however many are this. So it was bit by bit just giving meaning to those values, and then the routers and our devices all put things in the same order and read things in the same order. We all agree on that order. Done. We got IP and TCP handled. We got a handle on that. What do we do when we get to HTTP? So when we're parsing HTTP, we've been doing everything as text, but how did we even do that? It seems like we cheated already. So with this, we're going to use encodings. We got to talk about encodings, and then finally MIME types. Those are the 2 things we want to talk about today. So encoding text, like how do we even send text? We can't send text over the internet. I can't send the character capital R over the internet. It doesn't work like that. So we have to encode that into ones and zeros and then send the ones and zeros. And I assume most of you have seen this before. I don't think I'm breaking any new ground with ASCII, but just in case, let's do a very quick hopefully refresher, but if not, here's what ASCII is on this. So ASCII is going to map characters to numbers, and it uses 7 bits. It's a 7-bit encoding, and ASCII is this. So what we're going to do is put this chart out there. We all agree what ASCII is. It's this chart. This is the entirety of ASCII, and say every character that we want to send, like if I want to send a capital P, I'm going to send the decimal value 80 in hex, that's going to be 50, and send that value as binary over the internet. And then on the other side, they're going to interpret that as ASCII. They'll look it up on their chart. Well, they'll have code to do it for them. They'll look it up and say, okay, that's hex, hex whatever, 80, hex 50. It's going to get those, that 0, 0, 1, 0, 1, 0, 0, 0, 0. Hey, I remember my binary. It's going to get those ones and zeros, and then it's going to say, oh, that's a capital P, and interpret it as a capital P. So that's how we can convey text over the internet. We just map each character to a sequence of ones and zeros, 7 ones and zeros. Done. Easy peasy. Easy day. We just have a mapping. We call it ASCII. Cool. So if I want to send the string hello, which is the only thing we've ever sent over the internet so far, that's the only HTTP response. We didn't see any post requests, so nothing in the request yet, but we sent a response that said hello. It's the only thing we've sent so far. And when we send that, we're going to encode it as hex, which is just binary but more human readable. Really, what goes over the internet is this. And I say a 7-bit encoding, but we don't really talk in 7 bits in computer science and computers. We talk in 8-bit bytes. So the first bit of every ASCII byte is going to be 0. So every single ASCII character is going to have a leading 0. If you see a bunch of ones and zeros and somebody's usually making a joke, or somebody has a shirt that has a bunch of ones and zeros, and you notice that they're grouped in 8s and the first bit is always a 0, you know that they have some ASCII joke on their shirt or whatever. So it's an easy way that you can spot ASCII if every byte starts with a 0. Then we send the ones and zeros over the internet. So this is hello buzzing through the internet is going to look like this. HTTP headers are ASCII only. This is crucial for the functionality of the internet. So when we receive an HTTP request, or we send the browsers reading our HTTP response, we know the headers are always only ASCII. So we can look for the byte sequence /r/n/r/n, which, by the way, our CR is 0D, and our line feed. Our line feed is 0A. So if we see 0D, 0A, 0D, 0A, so 2 CRLFs, then we know that that's our blank line. That's the end of the headers. And we know everything before that has to be ASCII. So we can take all those ones and zeros and interpret them as ASCII and safely treat it as ASCII text. We know we're not going to get any errors there because it has to be ASCII text. Maybe someday headers will be able to be UTF-8. Probably not. I think that'd be too big of a change to make and break a lot of the internet. But HTTP headers, ASCII only. So this gets us started. The reason this is so important is it gets us started. We can read the ASCII headers now. The IP headers, the TCP headers, that was just straight binary. And now the next thing is the HTTP headers, and we know that that's ASCII, and we know that there's this byte sequence, CRLF, that indicates the end of the headers. We look for that byte sequence, everything before it, ASCII, decode it as text, and we're off. We're ready for things. So when we're checking the headers, well, I already got ahead of this one, but we can read the headers, decode as ASCII. We know what those ones and zeros mean now. And ASCII's pretty cool, right? But it's not great. It has strong limitations. It's a 7-bit encoding. That means there's only 128 characters, which is fine for English text. We have our capital letters, our lowercase letters, our numbers, our special characters, and then our control characters, tabs, spaces, our white space characters, things like that. It's fine. But if you don't speak English, it kind of sucks. If you want accents or umlauts on your characters, or if you have a language that doesn't use the 26-character English alphabet at all, you're screwed. ASCII just doesn't do what you need it to do. It's extremely limiting. And when we're talking about the internet, that's a problem because the internet's worldwide. It's global these days. We can't have a standard that really only fits English-speaking countries. That's not going to work for us. The internet's bigger than that these days. So enter UTF-8. UTF-8 is going to answer this problem, solve this problem for us, and solve it forever. UTF-8 is going to be able to encode just everything. There's plenty of room left in UTF-8. We've encoded every character anybody could dream up that they wanted in this. Languages where every single word is a different character, that's all in UTF-8. It's all stuffed in there. And with room, I believe, room to spare. Every emoji, everything's in here. All the accented characters. So this is how UTF-8 works. And the beauty, I'll start off with my favorite feature of UTF-8, the best thing ever that UTF-8 does, is that UTF-8 is variable width, so it's either 1, 2, 3, or 4 bytes. And if it's a 1-byte character in UTF-8, it's an ASCII string. It's an ASCII character. So if the value starts with a 0, if you're reading a byte and you're decoding UTF-8 and you get to the start of a character and it starts with a 0, it's an ASCII character. The remaining 7 bits are ASCII, which means any valid ASCII text is also valid UTF-8. So this is reverse compatible with ASCII, that UTF-8 is basically a superset or a super alphabet, a super protocol, I don't know the correct term there, of ASCII, which is extremely handy. It means we don't have to worry about switching from ASCII to UTF-8. If you support ASCII, you just naturally support UTF-8. You just don't take advantage of the 2, 3, and 4 byte characters, which is fine. You just still have valid UTF-8. It's great. If you need more bytes, the way the encoding works is the first byte for the character is going to start with a number of ones equal to the number of bytes for that character. So if the first byte of a character starts with 1110, that means that the character is 3 bytes, and the next 2 bytes will be continuation bytes, which will start with 10. And then all the X's are what represent the actual character for that UTF-8 character. We won't have to know the actual specifics of the protocol. I like showing this just because it's simple enough, it's straightforward enough. But a few reasons why I want to show this. And one is that this is a specific format. This follows a very strict structure. So if you have random data that is not UTF-8 encoded, that is not encoding text, it's not going to follow this structure. I mean, with high probability, it's not going to, unless it just by pure coincidental chance, it happens to fit this, which isn't going to happen. It's not something we can rely on at all. So if I have some bytes that represent, say, an image, which we'll run into later in the course. I say later in the course, but it's next week. And I read the bytes, I try to decode that as UTF-8, and I get the first byte of the image, and the first byte is 1, 1, 1, 0, and then 4 other bits. And then I look at the next byte, and I'm expecting it to start with 1, 0, and it doesn't because it's not UTF-8 code. It starts with like 0, 0 or something. Well, now I have a decoding error. Things break, and Python in that case is going to do one of two things. It's either, 1, just going to crash, or 2, it's going to attempt to decode. It's going to attempt to guess what you were encoding and decode with a whole bunch of encoding errors. So it's going to give you something that's not quite the bytes that you started with. So if you don't have text, do not try to interpret it as UTF-8. Do not try to interpret it as text, because this is a strict enough structure that it's going to corrupt your data or crash your program. In either one of those, depending on what exactly you're doing, what methods you're calling in Python, what the exact situation is, it's going to do one of those two things. Both of them are bad. Both of them mean your app isn't going to do what it's supposed to do. But one of them crashes. Obviously, that's probably better because you get to find the bug quicker. But the other one, your image just isn't going to display. Like, your image is going to be corrupt. So we have to be careful with this. If it's not UTF-8, don't interpret it as UTF-8. Oh, I meant to go to this slide. And the reason for this structure is that no character is a subsequence of another character. You can verify that yourself if you want, but I want to move on. So when we're sending data over the internet, when we're communicating over the internet, we are formulating our responses usually as strings. I mean, you can just work in bytes if you want, but usually we're going to formulate our response as a string. And then before we send that string over the internet, we have to encode it into UTF-8 bytes. We have to encode our string into bytes. Our string is language dependent. A Python str is not going to be understood by any other language. When we're sending over the internet, it's whatever language that browser's written in, probably C, or interpreted by the JavaScript in the browser, or JavaScript. Neither of those languages are going to understand a Python str. It's not going to work. So we have to encode it into UTF-8 bytes. And then when we receive data, when we get data from the browser, we get that as bytes. If you look at right from LO1 of homework 1, the constructor of the request class takes a byte string. It takes a sequence of bytes because that's what we get from the browser. We only get bytes. We have to decode it into a Python str so we can work with it as string. Or you can just live in the world of bytes again. You can just parse it as bytes too. When we get to homework 3, there's some things we will have to do in bytes. But that's where our encode and decode comes from. If you started the homework already and you're wondering, why do I have to have these encodes and decodes all over the place? This is why. It's converting bytes to strings and strings to bytes. That's what we have to do. You're applying the UTF-8 encoding on your strings or applying the UTF-8 encoding on your bytes to convert them to strings. And the default for encode and decode, I didn't give any arguments to these methods. You can give an argument, you can give it the encoding, but the default encoding is UTF-8 these days, has been for quite a while. It's a great standard that's going to be the default for Python. But if you want to put UTF-8 or UTF-8, I forget if there's a dash or not, as a string as an argument in these methods, that'll do the same thing as no arguments at all. But that's why the encode and decode is there. And then the content length. I mentioned this before, but now we can talk about this with more context. The content length of an HTTP message, whether it be a request or a response, is the number of bytes of the content. Everything after the blank line in your request or response. So after the blank line, everything before it's the headers don't count as part of the content length. Everything after the blank line is the body of the request, and that body, the number of bytes in the body is the content length, not the length of a string, because a UTF-8 character, if it's a non-ASCII UTF-8 character, which the homework has a couple of emojis in there specifically to test for this, the content length is going to be different than the length of the string if you have any non-ASCII characters, because they're going to be 2, 3, or 4 bytes for that one character. So we need to get the length of the bytes, not the length of the string. Luckily in Python, it's the same thing. It's just len, and then you throw the string or the bytes. It's going to tell you what you want. But make sure you encode the body that you're sending before hitting it with the len. Before you hit it with the len, so you're getting the length of the byte array, not the length of the string. Very important that we're getting the number of bytes, not the length of the string. Convert to bytes, then the length of the string. Okay, and then finally we get to MIME types. So the body, we haven't talked about the body of a request or response at all yet. The body is still just bytes. We said that HTTP headers are ASCII only, so that lets us parse the headers, including the request line, and the browser can parse our response line, our status line. But that only gets us up to that new line character. What do we do with everything after, or that blank line sequence? What do we do after that CRLF? We don't know anything about this, and it can be the body of a request or response can be encoded with any encoding. I mean, we talked about ASCII and UTF-8, and that's fine. But what if the body is encoded using JPEG? We're not going to be able to treat that as a string. We're going to corrupt the data. We're going to corrupt the bytes of that image if we try to interpret that as a string. So we have to leave the bytes intact of the body. If you notice on LO1, the body is still in bytes. All the other values are strings in the default values that I give in the constructor. All the values are strings, except the body is still in bytes. And this is why. If that body contains an image, how are we going to store that as a string? We have to just preserve that as bytes and then handle it based on what we're about to talk about, the MIME type. So the content type header is going to specify the MIME type of the data, and that's going to tell us which encodings are used to encode the bytes of the body. The MIME type, this used to be used for email, but it was adopted beyond that because it's pretty dang handy. And including in HTTP, we use this in HTTP. The MIME type is a type, and then a slash, and then a subtype. The one that we saw so far was text/plain. So the type was text, plain is the subtype. And some of the common types that we'll see, text, image, video, these are the categories of information, the categories of bytes that we can send. And some common type, subtype pairs. This is most of what we'll need throughout the course. It might be comprehensive, but I might be blanking on something. But text plain we saw already. Text HTML, CSS, and JavaScript are how we're going to send those three things. So when you want to send your HTML, you get a request for your HTML. You go to your HTML file, you read the contents of it, put the contents as the body of your response, set the content length to the number of bytes, and then the content type to text/HTML, and then the browser is going to interpret that as HTML, kind of. We got to talk about a few things before that, exactly. Image.png, image.jpg, video.mp4, and then application JSON. This should, if we could go back, as an industry and change this would be text/JSON. But back in the day, it made sense for it to be application JSON, but too late to change it now. So application JSON if you want to send JSON data over the internet, which we do. In Homework 1, there's a few cases where we're receiving and sending JSON for the chat messages. Okay, and then the content type header, we're going to see this even more so with cookies on Wednesday, but each header can have additional directives associated with it. So our content type, the first value of this header has to be the MIME type, but we can add extra directives with a semicolon and then key value pairs with an equal separating the key and value. So if I want to specify the encoding, which for some frickin' reason, UTF-8 is not the default of the internet yet. So we do have to specify UTF-8 as our char set, our character set. So char set equals UTF-8, all lowercase on UTF, 8 on UTF. This has to be exact. I've had many office hour visits where this isn't exact, and you'll know if it's not exact because your emojis, the 2 emojis that should show up, won't render properly on the front end. If your non-ASCII UTF-8 characters are not rendering properly, there's probably something wrong with this, and the amount of frustration on students when this dash is an underscore. They visit me in office hours. They're like, man, I've spent hours on this. I cannot figure out why it's not rendering right. I have everything perfect. And I look at it for 2 seconds. This is the first thing I check on my progressions. First thing I check, and then 2 seconds, I'm like, yo, that's an underscore. It needs to be a dash. Oh, man, the despair on their face. They're happy to get the bug gone, but they're like hours, and you solved it in seconds. Just make sure that this string is exact. It's going to save you some of that anguish. Lowercase UTF-8, -8, equal sign here, char set, make sure it's spelled right. It all has to be exact or else the browser is going to panic. We have something called MIME type sniffing. How are we on? We're not doing great on time here. I want to at least get through MIME type sniffing. So the MIME type can kind of be wrong. And if it's wrong, the browser's going to try to figure it out. If you say text/plain and your content is actually HTML, the browser's going to be like, it kind of looks like HTML. I'm going to render that as HTML. This is generally something we don't want the browsers doing. So we want to disable this, and we disable this by setting a special header, X content type options to no sniff. And this is going to tell the browser, look, I know you have this cool feature where you sniff out MIME types. I don't want you to do that. I don't want you to figure out my MIME types. I got my MIME types right. Just take my MIME type as is. And then if your MIME type is wrong, the browser is going to give you an error, which we'd much prefer to get that error than have it figure it out for us, for a few reasons. One, if my MIME type's wrong, I want to know about it so I can fix it. Like, I have a bug in my code. I want to fix that. I want to fix my bug. If the browser figures it out, one of the issues that this can create is I'm doing all my testing in Chrome. Works great in Chrome. Chrome's MIME type sniffing finds my mistake and just says, I know what you meant. And then I release to my users.